Assalamualaikum warahmatullahi wabarakatuh. Before we start our presentation for today, I would like to introduce every members of this group. First of all, it's me, Muhammad Nazim bin Muhammad Remi, student ID 2026117241.
Greetings and salutations. My name is David PANCRATIUS and my student number is 2026120901.
Assalamualaikum and hi, my name is Muhammad ADLI bin Muhammad YUSOF with student number 2026112575. Thank you.
Now, we move on to the introduction of our project. So, our group project is titled The Best Fit Quadratic Curve Between Variable Student Study Time in Hours and Final Grade, G3, in 2 Portuguese schools. So the data we used was obtained from the UCI Machine Learning Repository Student Performance Dataset, where the study focused on studying the correlation between study efforts and academic outcomes of a sample of students from 2 Portuguese secondary schools based on numerous factors like study time, parents' education level, and so on. However, in this project, we will be using the study time hours as variable x and final grade G3 as variable y. For your information, the final grade G3 is based on the Portuguese grading system, which is a numerical scale from 0 to 20, with 10 being the minimum passing score. In this report, we will be using the quadratic model to observe the data by doing manual calculations as well as using Maple software to obtain the best quadratic curve. The table in the slide shows the data obtained. Now, we move on to the methodology of this project for manual calculations. So firstly, we have to show that the system is inconsistent so that we can use the least square method. So to do this, we must first use the quadratic model to rewrite the data in the form of ax equals b to observe the data. After that, we are going to rewrite the data in the form of an augmented matrix. Then, we are going to use several elementary row operations, EROs, to reduce the matrix into reduced row echelon form, RREF. And so after doing all the operations, we will get that the final matrix where row 4 until row 10 are false statements, which tells us that the system is inconsistent. So, and because of this, we can proceed to use the least square method, where we will be using the equation A transpose AX equals A transpose B. Moving on, now we are going to be using the normal system equation, which is A transpose AX equals A transpose B. So we are doing this to get the value of A, B, and C so that we can obtain the equation of the best fit quadratic curve. So first we rewrite it in the form of the equation. Then we are going to rewrite the equation in the form of an augmented matrix, and then reduce the augmented matrix using EROs until it is in the form of reduced row echelon form, RREF. And so after doing all the necessary elementary row operations, we will get that A equals to 335 over 62, and B equals to 48 over 31, and C equals to 29 over 62, which gives us the equation of the best quadratic curve, which is y equals to 335 over 62 plus 48 over 31x plus 29 over 62 x squared.
Moving on to our next step, once we have our calculated values, we need to assess how well our model fits the data. To do this, we calculate the error vector, which represent the exact difference between our observed real values and the values calculated by our model. As you can see at the top of our handwritten notes, the formula is expressed as E equal to Y minus AS. Then we subtract all the product of our design matrix A and parameter vector X from our outside data. Then we perform the matrix multiplication. After that, we will get a new column vector. By subtracting these calculated values from our real values row by row, we will obtain our final error vector, shown right here on the middle right side. If you can see, each element in this vector tells us the residual error for that specific data point. Finally, we need to find the magnitude of this error vector, which is why we need to understand the total overall across all the value in the entire data set. And then, as stated in the text definition, we calculate by taking the square root of all the summation of the squared value from each individual data point in the error vector. We plug in our values, square each fraction to eliminate any negative signs, sum them all up under the radical and simplify. And this brings us to our final total error magnitude of square root of 939/62.
And now we move on to methodology for Maple comments. You're doing plot data point first. So here we have our comment, which is first we have to, the basic one is to restart. And to use the linear algebra and plots package, we need to write down with linear algebra in bracket and with plots. So first we take our x from before and declare it as our a. Here we did all in the column, which is 2, 3, 1, 4, 2, 3, 1, 2, 4, 2. And this is our output that we should get. After we're done declaring our A, it's time to declare our B, which is 11, 14, 9, 18, 10, 15, 6, 12, 20, and 8. And this is how our output would get. Now that we have our matrices for A and B, we can now plot it, point plot. Now we declare it as D, and inside we need the A and B, and the symbol we declare it as circle, and we uses the color red, and make the size of the point as 10. After we done declaring that, we just wrote down display D and we will get our output here. Now we need our matrix of 1 to pair with our A and B. Since our A and B has 10, so we need 10 of ones. So here A1, declare it all 1, there's 10 of them, and our output should be as simple as that. So now we want to put all of it together, so we declare it as x. So we have our A1, our A, and the third one is to find A times A. So here we can see in the output is 2 times 2, which is 4, 3 times 3, which is 9, 1 times 1 is 4, 1, 4 times 4 is 16, and go on until we get our output looks like that. And here we declare our y, which is we take back the x from before and put b behind, and we should get that output. Now it's time for us to do RREF, or reduced row echelon form of y, and we should get that where our leading one should be in the first 4 row. Using our x, we want to find the transpose of x. So here we declare our transpose of x as xt, and we should get output such as. Now we need to declare an x, the transpose of x times with our x, and since they both have a, if I'm not wrong, x has 3 column and transpose x has 3 rows, so our output should get a 3 by 3. And now we can just go on and find our determinant of x, which is the determinant of the xt times x. To find our xty, we just multiply the transpose of x with our b. And now we just mesh it all together in one matrices. We declare it as M. And it's just that the x transpose that times the x and the x transpose times the b. We just put it in one matrices, and we will get that output. Now we want the our calculation to be wrote down in Maple. So just wrote it back down all of it, and we should get the equation such as that. And that is actually a quadratic model. Now from our M, we can do our RREF to find the A, B, and C. And here we got that A is 335 over 62, our B is 48 over 31, and our C is 29 over 62. Now we just take the equation and put it into our point plot that we did before and plot it, and we will get a line that curve from 7, I think it's 7.5 up until 19, and that being the y, and the x would be from 0 to 4. And that's it for our plot data points maple command.
Moving into the error calculation phase of our methodology, we begin by establishing our final answer U vector using Maple. As shown here, we define our solution variable, and then the Maple process this syntax directly, outputting the simplified rational vector you see on the right. These vectors serve as the foundational baseline for determining our model precision. Next, we need to determine the discrepancy between our observed data point and our model prediction. To do this, we calculate the error vector, which we label ERR as error. The maple command subtracts the product of matrix A and our answer vector from our true vector Y. The resulting output is a comprehensive column vector representing the individual residual or raw errors across all of our data points. Finally, to make sense of this individual residual as a single metric, we look at the total magnitude of our error. We execute this in Maple using the Euclidean norm command, specifically norm in bracket ERR, 2. This calculates the geometric length of our error vector, giving us final simplified magnitude of the answer above. This single value quantifies the overall accuracy of our calculation, showing us exactly how closely our model fits the dataset. As a conclusion, both values will obtain a similar result, although there may be some differences at the answer but still having the same value. And this project has successfully applied the least squared method to find the best quadratic curve, use the concept in manual calculation, and use the right command for maple execution to solve the problem.
And that is all from us. Thank you for listening.